Welcome back to question 3 of our series on hypothesis testing for a single mean. The question reads, in a managed care organization, the mean starting salary for males in entry-level non-clinical position is $29,500. We want to determine whether the mean starting salary for females in similar entry-level non-clinical positions is different from $29,500. In order to make this assessment, we randomly select 10 females whose job titles and responsibilities fit our criteria, and we record their starting salaries in thousands. So what you see here should be all multiplied by 1,000. Is the mean starting salary for females significantly different from those of males? What I will do is write down the hypothesis that the null hypothesis is equal to 29,500. So we're assuming that for the null hypothesis that it's no different than 29,500, and the alternative will be that it is not equal. So either it's lower or higher. Let's look at how many were sampled. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N value of 10 means that we can't use the z-test, but we have to use the t-test. Unlike in the previous questions, questions 1 and 2, we are not given the mean for this, nor are we given the standard deviation. We need to find those manually. And the formula that we use is this one. T is equal to x bar minus mu over s over the square root of n, where x bar is the average of the sample, which will be found soon. That represents the average for the males at 29,500. S we don't know, that's the standard deviation for this data. And N we do know. So we have to find out what this is and what that is. Now that we understand the formula, let's go ahead and find the average for this data. I won't be doing it manually. I'll use a computer program to help me find the average, because I'm assuming you already know how to do that. And the same thing with the standard deviation. You should end up with a mean of 28,200. So this is 28,200, and the standard deviation of 3,841.87. Okay, we're good to go for the next step. This I'll replace with 29,500 and n with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just as before, if we're doing the t-test, we need the degrees of freedom. So df is n minus 1. 10 minus 1 is 9. Okay, we'll need that later when we read the chart. For now, let's find out what t observed will be. Using our calculator, 28,200 minus 29,500 divided by 3841.87 divided by the square root of 10. This gives us a t observed value of negative 1.07. We need this value so that we can compare it to the t critical, which we'll obtain next using this chart. So negative 1.07, I'll use the same chart as I used in the previous question, degrees of freedom of 10, or 9 it was. And since they don't tell us the significance level, they don't tell us or specify, we'll use 0.05. I forgot to specify, but in question number 1, we also had a similar hypothesis where it was equals and not equal to. And whenever that's the case, you use a two-tailed test. So we'll be using 0.05 right here, this one. It's two-tailed as opposed to one. So make sure that you know how to read this properly. And this dips down to 2.262. That will be our t critical. T critical is 2.262. And remember, this number is negative, so that should also be negative. As you can see, that t observed is greater than t critical. When that's the case, using the t-test, you do not reject the null hypothesis, which means that the salaries are not any different than what the industry standard is at 29,500. There's insufficient evidence at 0.05 that they are any different. And to show this visually on a t-distribution chart, it would look like this, where 2.262 would be over here. That would be the rejection region. And over here, negative 2.262 and positive 2.262. And it doesn't fall in that region. That's the answer to question number 3. If you'd like to see more examples where rather than using a single mean, we use two means, make sure that you watch our next couple of videos where we cover those types of examples. Hope to see you soon.